Alright, this is the fun video. We get to talk about one-to-one onto functions and bijective functions. One-to-one functions are also called injective functions, and onto functions are called surjective functions. So let's get right into this. What does it mean to be one-to-one? It means that if x is not equal, or say x1 is not equal to x2, then f of x1 is not equal to f of x2. So basically, what this means is that if we have an x in here, let's call these x1 to x2, and we have some output y1 and y2. If x2 maps to y2, then this x1 is never going to map to y2. You'll never have two elements in the domain that map to the same element in the codomain. And in proofs, what we do instead of showing that if x is not equal to x2, then f of x1 is not equal to f of x2, we simply do the contrapositive and we show that, okay, so suppose f of x1 is equal to f of x2, and then we prove that x1 is equal to x2. So let's do an example of that. Let's take f of x is equal to 3x minus 2. So what we say, okay, we say f of x1 is equal to f of x2, which means that 3x1 minus 2 is going to equal 3x2 minus 2. And we can bring the 2 over to the right side, so we're going to get 3x1 is equal to 3x2, and then we can divide by 3, and we find that x1 is equal to x2. So here's the thing, if f of x1 is equal to f of x2, then we find that x1 is equal to x2, therefore we know that this function is going to be a one-to-one function. That means that any value we put into x is going to have a unique output. That is, if we pick two different x's, they're never going to get the same output. In fact, you see this on a graph that kind of looks like this. No matter where we go, say if we pick an x here and an x here, their outputs are going to be different y values, which we can see here. So this will be y1, and this down here will be y2. They're different values. So a nice good chart of a one-to-one function. If we have the set of x's here and the set of y's here, I'm going to make this a box. It might look like this. So it doesn't necessarily cover all of the possible y values, which we can see here. These simply are not covered here, these y values, but it covers all the different x's, and they're all going to be different y values. Let's try f of x is equal to x squared. Okay, so we start off by saying f of x1 is going to be equal to f of x2. Okay, so x1 squared is going to equal to x2 squared, which, let's take a look at this. This means that plus or minus x1 is going to be equal to plus or minus x2. Well, this doesn't necessarily mean that these two values are equal, because what we can do is we can say, okay, the negative x1 is equal to x2. And because we have a negative value equal to another one, they are not the same value, so this function is not one-to-one, which we can see in a nice graph here. So, you know, the x squared function. If we take an x point here and an x point here, we see that their y values are exactly the same, even though we have different values of x. And this means that the function is not one-to-one. So that's a little bit interesting. A function that's not one-to-one. And all that means is that two different values in the domain will give us same answer somewhere in the codomain. It just means that the f of x does not always produce a unique number as an output. So 1-to-1 just looks for unique numbers. That's all it really does. Is it says, okay, if we have an x, then it's going to produce some unique number once it comes out of the function. Onto functions are a little bit different. And they're a little bit more challenging to prove at once and sort of wrap your head around what you have to do completely to prove some of your questions. But basically, if we have a function from x to y, it basically says that all elements in y have some x that you can put into the function and you can get to y. So if we have our little codomain, we call this y, and our little domain x, and we have a function f, this whole domain here can be gotten with elements in x. So this goes there, and the whole codomain is going to be done, which means essentially that the codomain is equal to the range. Now, this can be a little bit difficult to prove. You're saying, wait a second, how do I prove this? So let's go right into an example here. We have f of x is equal to 5x plus 2. I'm going to rewrite this as y is equal to 5x plus 2, and basically what we do is we solve for x. Okay, well we have y minus 2 is equal to 5x, so y minus 2 over 5 is equal to x. So here's the question. Is it on 2 in the set of integers, and is it on 2 in the set of real numbers? Well, suppose that y is equal to 0. Then we're going to have that x is equal to negative 2/5. So, if we can only work in integers, then the only possible way to map x onto 0 is to plug negative 2/5 into the equation, but that is not an integer, therefore it's not on 2 in the set of integers. However, in the set of reals and rational numbers, it is going to be perfectly acceptable, because you can see that any value of y that you plug in, you're going to get some x value that can be put into the function in a real or a rational number. So all this says is that no matter what the value we put in for y, there is an acceptable x that can be plugged into this function that will produce that y. And that's all we've shown here. And the easiest way to prove that something is not doable is to find one example and say that's not okay. That's what we did for our integers here. We picked y is equal to 0, and we saw that, hey, if we want y to be equal to 0, we need to have a rational x value, not an integer value. And because we can't do that, we know that it's not on 2 in the integer plane. However, it's totally fine if we give it acceptable real numbers or rational numbers. So that's pretty cool. Now, if a function is both onto and 1-to-1, we call the function bijective. It's also known as a 1-to-1 correspondence. Of course, I really hate that term. It doesn't sound very mathematical, and we have really cool words for these, like bijective. Don't you love the word bijective? It sounds so cool, like, yeah man, this relationship's totally bijective, as opposed to saying, yeah man, that relation's totally a 1-to-1 correspondence. Like, it doesn't have the same ring to it. And basically what that says is that each x in our domain maps exactly to one y in the codomain, and it hits every single y value. So if we have 3 elements in the domain, we have 3 elements in the codomain, and each of these will map exactly to 1 in the other. What this means is that, okay, say we have 4 elements in x, and only 3 elements in y, then we can't have a bijective relationship because we have this x that isn't being mapped to anything. And that breaks the 1-to-1 condition. So this is not 1-to-1, which I didn't write any. I'm just going to write 1-to-1 with numbers, even though you shouldn't do that. Now, what about the case where we have, say, 3 elements in x, but we have 4 elements in y? Well, okay, we have a nice mapping here, we have a nice mapping here, we have a nice mapping here. So clearly at this point, it's 1-to-1, but it's not on 2, because it is missing this element right here, so it's not on 2. So these are other ways of looking at functions. So a 1-to-1 function, the number of elements in x is always going to equal the number of elements in y. In functions that are not 1-to-1, the number of elements in x is going to be greater than the number of elements in y. And in functions that aren't on 2, the number of elements in x are always going to be less than the number of elements in y. So that's another way you can look at things, is through cardinality of sets. But that's not quite all for this lecture. We're going to talk about inverses. This is going to be really quick. Basically, if we have a function that maps x to y, then the inverse function just maps all the elements in y back to some element in x. And you are required to have bijective functions to do this. Because if there is a 1-to-1 correspondence, that means if I take my x1, I'm going to get to some place in y1 through f, and then I can go backwards and get back to x1 if I just take the inverse of it. So that's all the inverse relationship is. In fact, you see some really cool properties, is that if you take the inverse of the function at x, you're just going to get x back. And it doesn't matter which way you take this, you will always get back the same element that you started with. So that's a nice cool little property. And in fact, you see here, if you just draw the picture, okay, well, we have this value x here, and we go through the function, and it goes to some place in y, okay, and then the function takes it backwards. So we get back to the same point. Similarly, if we start at this y1, and we go to the x domain, and we get some value here, and then we take the function and write it back, we get back to y. So that's a cool property of inverses. And again, I reiterate, a function must be bijective to have an integer. I mean, an inverse. Otherwise, things can be kind of weird. For instance, let's say that f of 1 maps to 2, and f of negative 1 maps to 2. Okay, so this is pretty nice. But then, what does f of the inverse of 2 go to? Does it go to 1 or does it go to negative 1? Because it can't go to both. So what does it go to? And that's a difficult question to answer. So we say, well, okay, let's just say no to non-bijective functions and only work with bijective functions for inverses. So that's inverses. It's not too bad. The biggie really is proving bijectivity. For instance, if the question is, does this function have an inverse? The real question you're asking is the original function bijective? And if it is, you can claim, yeah, okay, it has an inverse. What is the inverse? Well, you got the inverse by doing the onTo question, because you solved for the inverse. Pretty cool, right? Anyways, if you have any more questions on this, just leave them in the comments and I will answer them as quickly as possible. I hope you learn this a little bit more easily than just reading a textbook, because functions can be pretty difficult if you haven't been explained them verbally, because sometimes they look really complicated, but it's just something you've been doing pretty much in high school. It's just got a cool little abstraction label on it that makes it a little bit seemingly harder than it is. So That was inverses and one-to-one onto and bijective functions.